Okay, sorry about the pause. I'm trying to not let these videos get too long so that I can still post them on Moodle. So, alright, so we were talking about protons being discovered by Rutherford. Oh, PowerPoint has stopped working. That's awesome. Okay, let's see if I can get it back up and running here. Sorry about the pause in the video, everybody. Just, you know, do whatever you have to do. Get something to drink. Well, don't do that. We're almost back where we were. There we go. Nope. Almost. There we go. Okay. So, as I was saying, protons got discovered by Rutherford. That's with the gold foil experiment. And then neutrons were discovered by Chadwick a few years later. Chadwick came along and realized there was something else in the nucleus besides just the neutrons, or besides just protons. And that's where the neutron was discovered. Shortly after the neutron was discovered, the idea for the atomic bomb and nuclear fission was developed. Because once the neutron was discovered, then we were able to isolate the neutron and start shooting it at big unstable atoms and making it split. And that's the idea behind fission, and we'll get to that in the next unit. Okay, subatomic particles. We got protons and electrons. Those are the ones that have a charge. Okay, this is just a summary of all the subatomic particles. All the big ones. There's smaller ones. There's subatomic particles, but these are the subatomic particles. Protons and neutrons have about the same mass. Neutrons are neutrally charged. The electron is significantly smaller. It's so small, in fact, we just ignore it. Okay? So there's a little chart that you have down here that's not very clear. Didn't copy very well, but that gives a summary of the charge and the mass of each of the different subatomic particles. Okay, so let's take a look at the sample problem here. Oh, we don't have the sample problem on here, but I'm just going to write it on here. It says the diameter of a US penny is 19 millimeters. The diameter of a silver atom, by comparison, is only 2.88 angstroms. Okay, and we want to know how many silver atoms could be arranged side by side in a straight line across the diameter of the penny. All right, so what we have to do here is basically just a conversion. Okay, an angstrom is 1.0 times 10 to the negative 10th meters. Okay, and we want to know, I'm sorry, it's 2.88 angstroms. So we got to do a conversion here. So we want to know how many silver atoms we could put across the diameter of a penny. So maybe we should start with 19 millimeters here and figure out exactly how many angstroms that is. Okay, might be easier to go from millimeters to meters, and then we'll go from meters to angstroms. I'll just put A and G there. I don't know if that's really a abbreviation or not, but there are 1,000 millimeters in 1 meter. Okay, that takes care of our millimeters. So now we're at meters, and we know that 1 times 10 to the negative 10th meters is 1 angstrom. Okay, and then we also know that the diameter of the penny, there are 2.88 angstroms in every 1 penny. Might be kind of a weird way to set that up, but that's the way you can use dimensional analysis to do it. Okay, so once you go ahead and calculate that, you got 19 divided by 1,000, then divided by 1 times 10 to the negative 10th, divided by 2.88. And that should give you a fairly large number. It's going to give you 6. Let's see, we've got 3 sig figs in our original numbers, so 6.60 times 10 to the 7th atoms. Okay? So that's how many silver atoms we could put in a straight line across the diameter of a penny. So that gives you an idea about how small the atom is. Let me go ahead and erase this now. It's not letting me do my circle erase thing here. Okay. So now let's talk about symbols of elements real quick. You guys are very familiar with this, but symbols of the elements are symbolized by one or two letters, okay? And so we've got mass number here, and I want you to put these on here. You've got the symbol of the element. The mass number is the one that's up at the top. That tells you the number of protons plus the number of neutrons, okay? And I think the atomic number showed up first on here. Actually, the atomic number, the number at the bottom, is the number of protons or electrons as long as it's neutral, okay? So as long as it's neutral, the atomic number will tell you the number of electrons as well. Mainly, it tells you the number of protons, okay? Atoms of the same element have the same number of protons, and the atomic number is symbolized by a Z. You might see that every once in a while. That's kind of a little bit older. I don't see that as much on the AP exams anymore, but you might see it, okay? So isotopes, we're talking about isotopes here. I'm not seeing some of the things that are on my notes here. Oh, here we go. Okay, I'm sorry. I just skipped right past it. There we go. The mass of an atom in atomic mass units, total number of protons and neutrons in the atom. Okay, and that's symbolized by AMU, so I think we know about that. That's the bottom number. Usually on the periodic table, it's usually the number that's a decimal. Okay, isotopes. Isotopes are atoms of the same element with different masses. I think we know that too. Isotopes are going to have different numbers of neutrons. Okay, so the thing that's different about them is not the number of protons. If you change the number of protons, you have changed the element. Okay, this number has to be 6 for it to be a carbon atom. Okay, but you can have different types of carbon because you can have different numbers of neutrons in there. So in this particular carbon, because there are 6 protons and this mass number shows us the number of protons and neutrons, that means that this carbon must have 5 neutrons in it. Okay, this carbon must have 6 neutrons. This carbon has 7 neutrons, and this carbon has 8 neutrons. Okay, so the way you figure that out, again, you just take the mass number minus the atomic number, and that'll give you the number of neutrons. Okay, so isotopes of hydrogen, that's an example there. So you can have, and actually you could have written down, if you'd written down the carbon example, that's fine also. Let's just go ahead and skip over this. If you want to write down the carbon example, that's probably the best one to write there where it says example, if you didn't already do so. Okay, let's do a sample problem here. How many, and I'm just going to use this screen to do it, how many protons, neutrons, and electrons are in an atom of 197 AU? Okay, so gold has a mass number of 197. So the question that we have to ask ourselves here is, sorry about that, the question we have to ask ourselves is, how do we know the number of protons that there are in AU? Alright, so if we look at our periodic table here, periodic table is going to tell us, oh, it went away. The periodic table is going to tell us AU, if we find the symbol for AU, that it has an atomic number of 79. Okay, so if we're going to write the complete symbol for AU, it's 197.79. Okay, and again, that's going to tell us everything we need to know about the protons, neutrons, and electrons. All right, so protons first. The number of protons just comes from the atomic number. The atomic number is 79. It's the number at the bottom. So that's how many protons we have. The number of neutrons is a little bit tricky. We'll come back to that one. Number of electrons is also easy as long as the atom is neutral. And here it is, because there's no charge here. All right, so we just assume this is neutral, so it also has 79 electrons. Now to find the number of neutrons, all you have to do actually is take the top number, the mass number here, minus the atomic number, and that'll give us the number of protons, sorry, the number of neutrons. And that's going to be 118. Okay? So that's how that works. Fairly simple stuff. Okay. Magnesium has 3 isotopes with mass numbers 24, 25, and 26. Write the complete chemical symbol for each of them. Okay, I'm just going to do this at the bottom. Ignore this atomic mass stuff. We'll come back to that in a second. So we're going to write the complete chemical symbol for each. So each of them is going to start with the Mg, okay? And then the atomic number for each of those magnesium atoms, we'd have to look on the periodic table for. If you look that up, each of those has an atomic number of 12. So we're going to put 12 on the bottom, okay? And then one of them has a mass number of 24. The next one has a mass number of 25. Now, these are all going to have atomic number 12. Otherwise, they're not magnesium, because the atomic number is the number of protons. Number of protons is always the same, okay? So there's the three chemical symbols we need to write for those. And then it wants to know how many neutrons are in a nuclide of each isotope. Nuclide just means in a nucleus. It's a weird way of asking that. So they're asking for the number of neutrons in each of these, okay? And again, pretty easy. This is going to be 12 neutrons because it's 24 minus 12. This one would be 13 neutrons, and this one would have 14 neutrons, okay? So that's how those examples work. Hopefully pretty easy stuff. All right, atomic mass. The next thing on the next page. Atomic and molecular masses can be measured with great accuracy with a mass spectrometer. I'm not going to talk a lot about that right now, but that's a piece of equipment you can use. Sorry, I'm trying to get through this quickly. Average mass. Now we got to talk about that for a second because we use average masses in calculations because we have a lot of isotopes, okay? And we want to fairly represent each of those isotopes and their abundance in nature, okay? So an example here, well, let's see, average mass, I have that part up there, calculated from the isotopes of an element weighted by their relative abundances, okay? This is basically just a percentage thing, okay? And I think you're going to remember this once we get to it. And I realize that last one cut off on you here. Okay, so here's the example. You've got neon found in 3 different isotopes in nature, neon 20, neon 21, and neon 22, okay? So the way that you would find that average atomic mass is you would take the mass of the first one, you would multiply it by its natural abundance, okay? But the natural abundance, you don't want to multiply by the percent. You need to change this to a decimal, okay? And the way you do that is just by moving the decimal place over twice, and that gives you 0.904838. So that's where that number comes from, okay? Then you're going to add that to the second mass times its natural abundance. Now this is a percentage right here, this number, so you got to swing that over 2 decimal places to the right, and that's where this number comes from, okay? And then same thing, 21.9914, swing that over 2 decimal places to the right, and that's going to give you 20.1797 AMU, okay? So that's how that works. Okay, I'm sorry this thing is so scattered. I am trying to do this in the morning, and it's hard to do that when people need things. So, anyway, moving on here. Let's, actually, let me shrink this for a second here. We'll do this one in Notebook. Nope. There's Notebook. That way we have a little bit more space to write. So this sample problem, it says naturally occurring chlorine is 75.78%, 35 Cl, which has an atomic mass. Okay, I don't need to read all of this. But basically there's 2 different main isotopes of chlorine. Okay, one of them is 75.78% abundant, the other is 24.22% abundant. So to find the AMU here, all we're going to do is we're going to take, this is really simple, we're going to take the mass of the first type, which is 34.969 AMU, and we're going to multiply that by its percent abundance changed into a decimal, so that's 0.7578, okay? Then we're going to add that to the 36.966 AMU. We're going to multiply that by its percent abundance, which is, again, changed to a decimal, 0.2422. Okay? And once we work all that out, sorry, I'm working it out on my calculator right now. You probably are too. Fun game would be to see if you can beat me. Alright, 35.45, which if you look on the periodic table, that's right about what chlorine is. Am I being sloppy here with my rounding? Now our percentages are 4 sig figs, so we'll go to 4 sig figs, 35.45 here. That's the average atomic mass of the chlorine, okay? That's how we find those average atomic masses. Alright, that's enough of that. Let's get this back up. Okay, now let's talk about the periodic table. We'll do this really quick, okay? It's a systematic catalog of elements. And the elements are arranged in order of atomic number. That's not originally how they were arranged when Mendeleev made his periodic table. He arranged it by atomic mass. Once we learned about the proton, it was much easier to arrange them by number of protons because that's different for every element. Okay, the periodicity here. When you look at the chemical properties of the elements, you're going to notice a repeating pattern. Okay, so in other words, we go usually 8 across, and then it starts to repeat. Okay, and again, once we get into period 4, period 5, period 6, then we have the D elements in there, which we'll talk about a little bit later. But they start repeating properties. So you look at lithium. It acts a lot like sodium. Sodium acts a lot like potassium. Okay, so we have these repeating properties that happen here chemically. The rows on the periodic table are called periods. And again, I think I told you the way to remember that last year is that a sentence is read left to right. There's a period at the end of a sentence. Okay, so periods are left to right. And hopefully that helps you on that. Whoops, columns or groups. Okay. So groups, notice the word up in group. Okay, so a group is up and down. Hopefully that helps you remember those. Elements that are in the same group, they're going to have similar chemical properties. There are certain groups that you might want to know the names for. I'll tell you the ones that I really care that you know the names for: the alkali metals, alkaline earth metals, the halogens, and the noble gases. The chalcogens, I'm not even sure how to say that. That one doesn't come up very often, but you might just want to be able to recognize that that's the column that has oxygen in it. Okay. Nonmetals are going to be on the right side of the periodic table. We learned that last year. You've got your stair-step line here that separates the metals and the nonmetals. Did I draw that in the right place? Actually, I think I drew that one over from where it's supposed to be. Sorry about that. I think it's supposed to be right here. Okay, so that separates the metals from the nonmetals. Notice the things that are right on the stair-step line are grayed out because that's called something else. That's called the metalloids. Okay, the metalloids are the ones that are semiconductors. That's supposed to be semiconductors. Sorry about that. But those are the ones that act like metals and nonmetals sometimes, just depending on the situation. And then you've got your metals, which is the majority of the periodic table. That's on the left side of the chart. Okay. So then our last sample problem here. Let me go back to. Why is it doing this? There we go. Go back over here, and we'll do one more example problem real quick. Which of the following would you expect to show the greatest similarity in chemical and physical properties? B, Ca, F, He, Mg, and P. Okay, so the following elements, which ones do you expect to show the greatest similarity? Okay, so we're basically just looking for things that are in the same column here. Okay, now notice Ca and Mg, both of those are alkaline earth metals. They're both in the second column. Okay, I don't think anything else in this list is in the same column. So those are going to be our two, okay? You're looking for things that are in the same column. So again, pretty simple stuff. I think you guys remember this. Not too bad. That's it for today. We will pick up on this after the weekend. Hope you're enjoying your weekend watching a video. Okay, bye.